Hello, everybody. Welcome to our introduction to the lab for weeks 4, 5, and 6. So we got a few weeks to do this lab, just as we did the previous lab. We're going to be talking about making images with lenses. So you'll have a setup where you can take a lens, and it's a converging lens. So we're going to be using a converging lens, and so that focuses light, it bends light toward the axis, so it bends light down toward its focal point, this direction. I'll draw you some pictures in a moment that will explain this a little bit more. But if this is your lens, we'll call S the distance between the object. The object is what you're making an image of. So you've got some sort of object there. It could be this piece of chalk. It could be the arrow that I've drawn right there. That's an object. For our purposes, objects will be real. Now you could have virtual objects that aren't actually there, and those objects would be made, they would be the images that are formed by other lenses. So once we put other lenses in combination, you could have that occur. We won't be doing that in this lab. We just have the single lens. So we're looking at the properties of a single lens right here, and to say we're using a real object. In your case, it's a lighted arrow, and that lighted arrow, the light from that arrow is going to shine through the lens. And we got a couple of rules that we'll draw here. We're not going to be doing much of this in the lab. If you read your book, and you should have, you have some homework out there that's due in the book, to say if you have a light ray that comes in, starting at the tip of this arrow, if it comes in parallel to the axis, it will be refracted. Remember, we've just spent a few weeks looking at refraction. So now we're taking that glass that we know the index of refraction of, and we're making special shapes out of that glass in order to bend the light the way we want to bend this light. And it's going to bend this light, it's going to deflect this light down through the focus. Okay? So that's the definition of the focus right there of that lens. The focus takes parallel light rays and bends them, refracts them through the focus on the other side of the lens like that. So there's a focus on either side. That's your focal length of the lens. That's what you're going to spend part of this laboratory exercise trying to figure out, is what is the focal length of the lens that you have. A light ray that goes through the middle of the lens is undeflected, and a light ray that goes through the focal point on this side comes out parallel on the other side. So let's just act like this lens is bigger than what it is, right? And if it goes through the middle, it's going to come out over here undeflected. And so you're going to make an inverted image over here, and that inverted image is a real image. It's actually there. You put a screen there, and you can see it. Now you could have a virtual image that you have to trace the light rays back with your eye and see where they look like they're coming from, the point from which they originate. That's a virtual image, but this is a real image, and you'll put a screen right there and you'll measure it, okay? This is a real image as long as this object is outside the focal length. If S is greater than F, you get a real image over here. If not, you don't. And so you'll have a virtual image, and we can draw that in a moment if we want to draw that in a moment. Maybe we'll wait till lab to draw that, take a look at that. So for a converging lens that bends light toward the axis like this, F is greater than 0. And as long as S is greater than F, then S prime, you get a real image. This is S prime is the image distance over here. And that's that distance that you have out on this side is where that real image is formed. And S prime is greater than 0 if it's on this side. If it's on the side the light's moving to, S prime is greater than 0. And S is greater than 0 as long as it's over on this side. If we had this lens, let's try it. Let's see if we can draw this. Let's say, there's our focal length, our focal point. And let's put our object inside here. Now it looks like a ray that would have come from the focal point would get deflected out parallel. Okay? And a ray, let's do it that way, a ray that goes through the middle is still undeflected. Let's trace this back. Okay? And a ray that is aimed toward the other focal point would come out, no, a ray that is parallel would come out looking like it was traced toward the, let's skip that. let's just draw that 2 right here. I don't want to get too far down this path to say, this ray. We're not going to be working in here. This is a virtual image. It's not really there. If your eye was here, it would look like you could trace this back to. You could have all of these points of light coming together right here. We're getting sidetracked here because we're not going to be making these virtual images, and I intended not to talk about it, but here we are talking about it because that's what we do. And so anyway, you've got your you've got this situation over here where you want to keep this outside of your focal length like this, but you can move this as far as you want to in and out outside the focal length. Otherwise, you're going to get in this situation where you have to the rays do not come together on this side of the lens, and you're going to have to trace them back to see where they cross in order to figure out where your virtual image is over here. You won't be able to put a screen there and see it. You need your eye in order to trace those rays back to see it. But that's not what we're doing, so let's move back over here and say the relationship, the thin lens formula, the relationship we're going to use is going to say that 1 over f, the focal length of the lens, is equal to 1 over s plus 1 over s prime. F is greater than 0. As long as you have s prime, as long as you have the image over on this side, the opposite side of the object, s prime is greater than 0 and s is greater than 0 as well, as long as you have your object over here. So you can solve this equation in MATLAB and or Kaleidograph. You can solve that equation for f in terms of an object distance and an image distance, and that's your first task in this lab, is to figure out what that f is. Now, if we put a diverging lens, we're going down a path here again that we probably shouldn't go down, but if we put a diverging lens in there, then that would take light. There's your f and your f here again, and we have our object here, and that would take light that comes in parallel and bend it out and make it look like it had come through the focal point on the other side, and it would take light that goes through the middle. This is what we were getting. We were mixing these two up a second ago, and it's undeflected, and light that's aimed toward the other focal point would come out parallel. These things cross right there, and you get a virtual image over here. So a diverging lens only makes virtual images, and f is less than 0 for a diverging lens. A focal length, we call that a negative focal length lens, and this is a positive focal length lens. But we're not using these in lab here. We're only making real images on a screen once again. So we've got another little diversion there from what we're actually doing in the lab. But it's interesting optics. It's optics we need to think about a little bit. We'll talk about more in lab as we move along. But anyway, your job is to sort of repeat the experience you had with the index of refraction lab. Do what you did, the skill you're building up is making repeated measurements in the sweet zone where you get the best measurements. And one of the things you have to do in lab is you have to figure out where you're getting the best measurement of f. So you want to measure f as many times as you can by varying s and s prime. So you slide your object around over here, and that's going to change your image distance, and then repeat it and repeat it and repeat it and repeat it, and make as many measurements as you can. So you can make a histogram of your values of f, fit a Gaussian to that histogram, and figure out what f is, okay, with an uncertainty on there with your standard deviation. So you want to do exactly what you've been doing here before with the index of refraction in terms of, well, not exactly, but in terms of the theory of the approach of making this measurement many, many, many times with many different values of s, leading to many different values of s prime. Now you realize there are s prime and s can be inverted here, right? That you can have, if s is one value and s prime is a different value, you can swap those so that s is the different value and s prime is the original value. But you have a lot of space to explore there, a lot of space to try to get f values, and your job is to figure out when you think you're getting the best data and really explore that region around the best data a lot. Just as you did with the index of refraction. It'll be tricky to figure out where that's actually focused, so you'll move s and then slide your screen around until you get good focus and measure s prime. Get a new s prime, new s prime, sliding the screen around until you get it focused, and to see what you can do with it. You may have some setups that work better than others. That's your job. That's the experimental magic you're working on, is to try to figure that out. Now, while you're doing it, you're also measuring the size of this object, the magnification of that object, the magnification of the lens, the magnification we're getting from that situation is the object size divided by the image size. So you want to measure that situation. You want to measure that object image size. Oh, good grief. It's the image size divided by the object size. And it's negative because this is an inverted image. It's upside down. Okay, so it's negative image over object. And we would expect, you can just do similar triangles here. You got a triangle, you got a triangle. You can do a similar triangles. You know your angles through there. And so you can do similar triangles and figure out that we would expect this to be equal to negative S prime over S. As S prime gets way out here, this ray has further and further and further to go. You're gonna make a bigger and bigger and bigger image. And so we want to test this image size, object size relationship, and to see. You're going to measure this directly, or you can measure that directly, and then try to compare it to this value that you're getting down here, and to see, okay, what's the difference between these? Are we getting the magnifications that we would expect to get? So I have a suggested way in the lab handout for you to think about doing that work, but you have other ways. You can go and do this other ways. If you want to go and do this other ways, that would be great. So anyway, that's the first part of the lab, is determining the magnification and the focal length of the lens with repeated measurements. Then we're going to go in, we're going to look for two different types of aberrations in the lab, and this is going to take you some time. So if you can actually do some of this work in the first week, that'll free you up for the next 2 weeks to be doing some of this other work, and that's probably important for you, because you probably need you want to get as much done as you can here, because one of the things we want to do is look for something called spherical aberration. And to do that, we're going to look to see if the focal length of the lens is the same as you move in and out from the center. So one of the things you might do, one good way to do this, might be to have a little circle of light. Cover the whole lens and only allow light to go through here, and here, and here. These could overlap a little bit. Just measure the position of the distance from the center, and to say, okay, here we go, we got this distance out. We can measure the focal length as a function of radial distance away from the center. So everything's covered. The only light you're getting is through here. The smaller that circle is, the better off you are. You can get more circles out there, and you can measure F as a function of radial distance away from the center of the lens, and to see if it's varying. If it's varying, you've got chromatic aberration in your lens. You've got spherical aberration in your lens. It's saying that you don't have the same focal length for all parts of the lens like that. Now, the smaller you make that circle, the more of those points, the finer you can measure are, and the better you can do. But the smaller you make the circle, the less light you're getting through there, and the harder it is to see your image, the harder it is to actually do this work. So this is going to take you a little bit of playing around. And so we want to do that. We want to measure F as a function of R and determine what that looks like, and probably graph that relationship to say F as a function of R out here to see what it looks like. And if you do it out different axes, perpendicular axes like this, and to say you get a different relationship over here, different focal length going across this way, going across this way, that's what we would call astigmatism. So you want to look for that too, but you understand there are other axes you could do out here too, and you can go the opposite direction and combine that data. So you have a lot of measurements you can make in order to try to get a good decent value of what F as a function of R is. You can measure this out this way, and this way, and this way, and this way, and all around through there. You can make lots and lots of measurements, and that's what we want to do. That's how we want to approach it. We want to have as many different measurements at different R's out through here as we possibly can, and to see, do they look consistent from one another? Does this R value look the same as this R value is the same as this one, is this one, and this one, and this one, and this one, all the way around? Is R varying here? Is R varying here? And so on. And so this is your task, to go and try to find astigmatism and spherical aberration in the lens, and to report. We'll talk about, we haven't gotten there yet, but we will talk at some point about how you report upper limits on things. So if you don't see any spherical aberration, I'm kind of guessing you will, but if you don't see any spherical aberration or any astigmatism, you can report the upper limit on that. But that's going to be our task over the next few weeks, is to start talking about likelihood, probabilities, likelihoods based on your uncertainties, on your sigma values, your standard errors, and then we can take that and start putting upper limits on things if we don't see something in it. So that's a skill we're going to work on as the semester develops. So we're measuring the focal length of the whole lens. Then we're measuring the focal length as a function of radial distance from the center of the lens to try to understand this spherical aberration and to see if that's the same in all directions that you move, to try to understand this concept of astigmatism. And then we're going to do one more step, and we're going to do chromatic aberration. And chromatic aberration says that not all wavelengths of light have the same focal length. So you want to go back to your full lens. You don't have to do these in the same order. You can do these in different orders. And you have different people in the lab group working on different pieces at the same time. But you want to go back to your full lens and cover up either the light source or the lens. Probably the light source is the easiest thing to cover up, with a filter that only allows certain wavelengths of light. And then you want to measure F as a function of the wavelength of light. And to say, is that consistent from one wavelength to the next wavelength to the next wavelength to the next wavelength? So you want to find out, does the focal length depend on the wavelength of light that you're using? And you have the same issue that you had before. Once you start filtering out a lot of that light, your images get dimmer, and it gets harder to focus this thing and to see where your image is. And we have, we don't have great filters. We have good filters. We have filter sets that you'll be looking at that you can use, and those filters don't allow just one wavelength of light through, but you don't want them to allow just one wavelength of light through, right? Because if they allow just one wavelength of light through, then you would have almost no light there at all. So they're sort of broad pass filters that allow, if this is the transmission, the percentage that gets through as a function of wavelength. They'll have a peak wavelength. They're funny filters that we have, and so they have different shapes. But they have a peak wave through, wavelength through here, across here. And so you might want to think about doing some kind of averaging that figures out what the average wavelength of light is that gets through that filter. Now, you're going to run into, here's where we run into complexities that haunt us always in doing experimental physics work. And it's good to start to recognize these things. And that is to say that if you just use the transmission of the filter, you would say, okay, I would take the average transmission and call that the wavelength of light that I'm going to use to measure the focal length. That's not bad. Except it's kind of assuming that you've got the same intensity of light. It's not kind of, it's exactly assuming you have the same intensity of light at all wavelengths coming in, and you don't. The intensity of your light source also has how bright your light is. How much light is there as a function of wavelength looks like that as well. And so you have to kind of think of the convolution of these two things. How much light is there? This times this. So one great thing you could do to do an analysis here would be to take break this up into wavelength bands, and in each narrow wavelength band, take the value here times the value there, and say that's what your value is, and then do that all the way across here, and then find the average of that intensity times transmission. It's really a convolution that we're doing. We'll talk more about this as we get in there. But you do the intensity times the transmission is equal to some number, and you do that as a function of wavelength, and then average over all of those numbers to get your average wavelength that's coming through there that you stick in here. Now that's a lot of work, and maybe you have time to do that work, and maybe you don't have time to do that work. But that's the way you have to recognize. That's the way you're going to need to do that to really understand what this is. To first order, you can just slap a whole bunch of different filters on there, and you can measure whether the focal length changes with different filters. If it does, then you know there is some chromatic aberration in your lens. If it doesn't, then you don't have any evidence of chromatic aberration in your lens, and this work is maybe less necessary. But it may be that these are so broad, and this is shaped such that you're not actually changing the wavelength as much as you think you are by putting those different filters on there. So doing a little bit of this work is probably a good thing. So there's a lot of work you can be doing here, a lot of interesting work to try to understand what's going on there. This is what we're doing. We're looking for chromatic aberration. We're looking for spherical aberration, and we're going to begin by just trying to measure the focal length of our lens using the thin lens equation. We got 3 weeks to do all this work. It's going to turn out not to be enough time to get it done, but it's enough time for us to really dig in and explore this question. So here we go. Physics 182, Classical Physics 2. For those of you who might be watching who aren't part of the class, I'm Professor Jeff Wilkerson at Luther College, and this is our second experiment in Classical Physics 2.